Hello everybody and welcome to today's lesson on adding and subtracting rational expressions. Today our objectives will be we will add and subtract rational expressions. Remember, rational expressions are essentially nothing else than fractions, and so let's remember what we need to do when we are adding fractions. We need to always have a common denominator, and in fact now we're going to practice finding the least common denominator, because if we have the least common denominator, then we have our fraction already in most simplified form at the end. And in order to find the least common denominator, we need to do a prime factorization of both denominators. In other words, we need to break them down into their prime factors. The prime factors of 25 are 5 times 5, or 5 squared, and the prime factors of 15 are 3 times 5. And now we will build our least common denominator, which will have all the factors that we found in it, and of each factor the highest power. Starting with the 5, we got a 5 squared and a 5, so 5 squared is the highest power. That takes care of these two. And then we still have a 3, so 5 squared times 3 is our least common denominator. And in order to get both denominators to the least common denominator, we need to multiply them by a fraction that contains the missing piece. Our first fraction has the 5 squared, but still needs a 3, so we're going to multiply it by 3 over 3. And our second fraction has a 3, but 1 5 only, so we are going to multiply it by the fraction 5 over 5. And now we can start multiplying this. We get 3 over 5 squared times 3 plus 5 over 5 squared times 3. When we do this, and you can see this here, we always end up with fractions that both have the denominator, which is our least common denominator, which essentially was why we did this in the first place. And now we can finally add up our numerators. So we get 8, and our denominator multiplied out ends up being 75, and this is our final answer. Our next example looks a little bit more involved, at least where the prime factorization is concerned. How do we do this? We just start by taking the denominator and dividing it by 2 as many times as we can, and if we cannot divide by 2 anymore, we use other numbers, try out the 3, try out the 5, and keep going like that. I already did this for you, so 1 over 1960 has a prime factorization of 2 cubed times 5 times 7 squared. And our second fraction has a prime factorization of 2 squared times 5 squared times 3 times 7. So let's build our LCD. And yes, LCD stands for least common denominator, not just for liquid crystal display. We have 2's, and of the 2 fractions, the highest power is 2 cubed, taking care of these 2. Then we have 5's, the highest power of that is 5 squared. We have 7's, 7 squared is the highest power here. And then we have a 3 left. And here goes our least common denominator. Now, what do we need to turn the first fraction to our least common denominator? We have 2 cubed, we need a 5, and we also need a 3. We have the 7 squared, so we're multiplying it by 5 times 3 over 5 times 3. And our second fraction needs a 2. It has the 5 squared, has the 3, and needs another 7. Okay, now let's multiply these out. 5 times 3 is 15 times 1. So 15 over 2 cubed times 5 times 7 squared plus 2 times 2 is 4 times 7 is 28 over 2 cubed, and there is a square missing for the 5 in our first fraction and a 3 missing. Now let's make this complete. 5 squared times 3 times 7 squared. There we go. Alright, add up the numerators and we get 43 over, and now we can also multiply our denominator out, and that ends up being indeed 29,400, which is our final sum of the two fractions. Now, of course, we can try doing this on the calculator. On the calculator, we might end up with a decimal. Sometimes we convert it back to a fraction. Not in this case, actually, and you're welcome to try it out. But also, this was just a warm-up so we understand how to do it with rational expressions, and that's what we're going to start doing now. So to add rational expressions with variables, we do the exact same thing as we do for regular fractions. We factor the denominators, and then we build the LCD. So let's practice this a couple of times before we actually start adding or subtracting these fractions. 2 over x and 2 over x plus 1. So what are our factors? X plus 1 is one factor. Remember that from factoring and from quadratic equations. X and 1 are not separate parts, they're not separate factors because they're being added. So our LCD, our least common denominator, is actually x times x plus 1. And that's what we would use if we wanted to add these two fractions. Let's look at our next example, and always remember we need to factor the denominators first if we can. X plus 4 is already factored, we cannot factor that any further. But x squared minus 16, if we take a better look at it, we see it's again our friend, the difference of perfect squares. So we are actually talking about the fractions 3 over x plus 4 and x over x plus 4 times x minus 4. Okay, let's build our LCD then. Our LCD will have to have an x over 4, which we have in both denominators, and the highest power is actually 1, so x plus 4 to the first power takes care of these two, and we also have an x minus 4, and that's our LCD, which, as it happens, is exactly the same as the denominator of the second fraction. Sometimes that's the case. Sometimes one of the two fractions already has a denominator that is the least common denominator of both. That may happen. If so, we're lucky, and we're going to move on. Let's try a couple more of these. First, let's factor our denominator if we can, and we can indeed. X squared plus x minus 2 can be factored into x plus 2 times x minus 1. And our second denominator, x squared plus 4x plus 4, is a perfect squared binomial because it's the square of x plus 2. So x plus 2, I'm not going to write it out twice, I'm going to show the exponent. So let's go and take our LCD. The LCD has to have an x plus 2 in it, but we have it with the power of 1 on the left and with the power of 2 on the right. So here goes that part. And we have an x minus 1. That's also part of our least common denominator. Check and done. In the next example, let's write these fractions out fully factored. 2 squared is actually what 4 ends up being, and nothing else to factor here. So on to build our LCD. We have 2's in here 3 times, but 2 squared is the highest power. We have x plus 1 twice, and x plus 1 squared is the highest power here. And then we have an x left. And of course we can go ahead and write this out a little neater. 4x times x plus 1 squared. Now let's go ahead and actually add some of our fractions here, but doing the same thing that we've done before, finding the least common denominator first. So what is our least common denominator on the left? It needs to have a 2 in it and an x squared, and that means that our first fraction needs to be multiplied by an x squared over an x squared, and the second fraction needs to be multiplied by a 2 over 2. And this will give us x squared over 2x squared plus 6 over 2x squared. Now we can go ahead and add our numerators. X squared plus 6 over 2x squared, and we cannot simplify anything more here. And now that we actually performed an operation, we need to make sure that we check for our domain restrictions. Domain restrictions, let's look at our initial problem, and x cannot be 0. This is our only domain restriction in this case. And we're done. Well done. And now let's move on to the next example. Let's first write these fractions in fully factored form. 3 over 2x plus x over, and we see that we can actually factor out 4x. 4 is 2 squared, and then what remains is x plus 3 in our parentheses. That's what we need in order to be able to actually find our LCD. So now the LCD actually is, we got 2's, 2 squared, we got x's, and we got the factor x plus 3. And that gives us our least common denominator. So our fraction to the left is missing a 2 and an x plus 3. Our fraction to the right actually has a denominator which is identical to the LCD. It already had all the factors in there, so there we don't have to do anything. So let's multiply this out first. We get 6 times the quantity x plus 3 over 2 squared x times x plus 3, and that is added to x over 2 squared x times x plus 3. And the 6 times x plus 3 we can actually distribute now, and we're going to get 6x plus 18. Now let's add these up together. 6x plus 18 plus x is 7x plus 18 all over 4x times x plus 3. Let's not forget to find our domain restrictions, and it's always easier to get them from our fully factored form here rather than from our original problem up here. So x cannot be equal to 0, and it can also not be equal to negative 3, and that's that. Okay, so much for this. Now go ahead and watch the second part of this tutorial.